Tonight, we're going to explore one of the most unsettling mysteries in all of science. There are 200 billion trillion stars in the observable universe. Most of them have planets. Billions of those planets sit in the habitable zone where liquid water could exist. Billions more have the right size, the right chemistry, the right conditions for life to emerge. The universe has had 13.8 billion years for that life to evolve, to develop intelligence, to build civilizations. Yet, when we point our most advanced instruments toward the cosmos and listen, we hear nothing. No radio transmissions. No signs of engineering on cosmic scales. No evidence of intelligence anywhere except right here on Earth. Complete silence. And by the end of tonight, you're going to understand why this silence might be the most terrifying discovery in human history. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what we know. The universe is vast beyond comprehension. Our Milky Way galaxy alone contains somewhere between 100 billion and 400 billion stars. Each one a potential sun that could have planets orbiting it. And the Milky Way is just one galaxy among an estimated 2 trillion galaxies in the observable universe. Do the math, and you get a number so large it becomes meaningless. There are roughly 200 billion trillion stars in the observable universe. That's a 2, followed by 23 zeros. And we now know that planets aren't rare. The Kepler Space Telescope revolutionized our understanding when it showed us that most stars have at least one planet. Many have several. Rocky planets similar to Earth appear to be common, not exceptional. Planets in the habitable zone, the region around a star where liquid water could exist on a planet's surface, are abundant throughout the galaxy. Conservative estimates suggest there could be tens of billions of potentially habitable planets in the Milky Way alone. And there are 2 trillion galaxies. Given these numbers, the question isn't whether life should exist elsewhere. The question is, where is everybody? This is the Fermi Paradox, named after physicist Enrico Fermi. During a lunch conversation in 1950, Fermi was discussing the possibility of extraterrestrial life and faster-than-light travel with colleagues at Los Alamos National Laboratory. The group was making rough calculations about the probability of Earth-like planets, the probability of life developing, the probability of that life becoming intelligent. The numbers suggested that intelligent life should be common. At some point in the conversation, Fermi reportedly looked around and asked a simple question. Where is everybody? The galaxy is 13.6 billion years old. Our solar system is only 4.6 billion years old. That means there were billions of years before our sun even existed, when other stars and planets were forming. Some civilizations could be billions of years older than us. If even a tiny fraction of those civilizations developed space travel, they would have had enormous amounts of time to spread across the galaxy. Even traveling at a fraction of light speed, even taking millions of years for each journey, a civilization could colonize the entire galaxy in just a few tens of millions of years. That sounds like a long time, but it's nothing compared to the age of the galaxy. So, where are they? We've been listening. The search for extraterrestrial intelligence, known as SETI, has been scanning the skies for radio signals since the 1960s. Radio telescopes around the world point at different stars, different regions of space, listening across a wide range of frequencies for any signal that might indicate intelligent origin. Artificial signals would have characteristics that distinguish them from natural radio emissions. They might have narrow bandwidth, confined to a very specific frequency rather than spread across a broad range. They might show modulation, variations in amplitude or frequency that could carry information. They might repeat at regular intervals. Natural cosmic radio sources, pulsars, quasars, active galactic nuclei. None of them produce signals with all these characteristics. An artificial signal would stand out. But after more than 60 years of searching, we've detected nothing. No narrowband signals. No modulation patterns. No repeated transmissions from the same location. The universe, as far as we can tell, is quiet. Completely quiet. The most famous false alarm came in 1977. Astronomer Jerry Ehman was reviewing data from the Big Ear radio telescope at Ohio State University. On August 15th, the telescope detected a strong narrowband radio signal that lasted 72 seconds. The signal was so striking, so unusual, that Ehman wrote, "Wow," in red pen on the computer printout. The signal came from the direction of the constellation Sagittarius. It was exactly the kind of signal SETI researchers had been hoping to find. Narrow bandwidth, strong amplitude, exactly at a frequency where radio transmissions would be least affected by interstellar medium. But the signal never repeated. Despite multiple follow-up observations using the same telescope and others, despite decades of searching the same region of sky, the WOW signal was never detected again. Without confirmation, without repetition, it remains unexplained, but not confirmed as alien. It could have been a terrestrial source, a reflection, interference from a satellite or aircraft. We don't know. And that's the frustrating part. Even when we get something interesting, it disappears before we can study it. Our own broadcasts have been leaking into space for about a century now. Radio and television transmissions, radar installations, all of these produce electromagnetic radiation that travels outward at light speed. An expanding sphere of human-created signals spreading through the galaxy. That sphere now has a radius of about 100 light-years, roughly 588 trillion miles, or 946 trillion kilometers. Every star within 100 light-years of Earth has been bathed in our radio transmissions. If any of those stars have planets with civilizations capable of detecting radio signals, they know we're here. But 100 light-years is tiny compared to the Milky Way. Our galaxy is about 100,000 light-years across, or roughly 588 quadrillion miles, or 946 quadrillion kilometers. Our signals have reached only a small bubble around Earth. A sphere 100 light-years in radius, in a galaxy 100,000 light-years across. We've barely announced our presence to our immediate neighborhood. And even those signals are getting weaker. The inverse square law applies to radio waves just like it does to visible light. Double the distance, and the signal strength drops to 1/4. Triple the distance, and it drops to 1/9. By the time our television broadcasts reach a star 50 light-years away, they're incredibly faint, barely distinguishable from the background noise of space. Detecting them would require enormous radio telescopes pointed exactly at Earth, tuned to exactly the right frequency, at exactly the right time. The chances of that happening by accident are vanishingly small. So, maybe civilizations are out there but haven't detected us yet, because we're too quiet and they're not close enough. But that doesn't explain why we haven't detected them. If the galaxy contains thousands or millions of civilizations, some should be broadcasting either deliberately or unintentionally. Some should be close enough for us to detect. Some should be advanced enough that their technology produces detectable signatures. But we see nothing. There are dozens of proposed solutions to the Fermi Paradox. Some are optimistic, some are pessimistic, and some are absolutely terrifying. Let's start with the most optimistic. The rare Earth hypothesis suggests that while simple life might be common, complex life is extraordinarily rare. This hypothesis points out that Earth had an unusual number of lucky breaks. We have a large moon that stabilizes our axial tilt, preventing extreme climate variations. We're in the habitable zone of a stable star that doesn't vary too much in output. We have Jupiter acting as a cosmic vacuum cleaner, its massive gravity attracting comets and asteroids that might otherwise bombard the inner solar system. We have plate tectonics that recycle carbon and regulate atmospheric composition over geological timescales. We have a magnetic field generated by our molten iron core that shields us from harmful solar radiation. Any one of these factors alone might not be necessary for life. But maybe you need all of them, or most of them, for complex life to evolve. Maybe planets like Earth, with all these characteristics, are incredibly rare. If that's true, then life might be common, but intelligence might be vanishingly rare. The galaxy could be full of single-celled organisms and devoid of anything more complex. Another possibility is the Great Filter hypothesis. This suggests there's some step in the evolution from non-life to spacefaring civilization that's extremely difficult. So difficult that almost no one gets past it. The filter could be in the past. Maybe the jump from non-living chemistry to the first self-replicating molecule is incredibly unlikely. Maybe Earth won the cosmic lottery, and we're the only place where this happened in the observable universe. If the filter is behind us, that's good news. It means we've already passed the hard part. But the filter could be ahead of us. Maybe every civilization eventually reaches a point where it destroys itself. Nuclear war, bioengineered pandemics, artificial intelligence that gets out of control, environmental collapse, nanotechnology accidents. The list of possible civilization-ending catastrophes is long and getting longer as our technology advances. If the filter is ahead of us, then the silence of the universe becomes a warning. It means that civilizations arise, develop technology, and then inevitably destroy themselves before they can spread to the stars. The galaxy might be littered with the ruins of dead civilizations, each one destroyed by its own hand shortly after developing advanced technology. This is the dark forest hypothesis, and it's one of the most chilling solutions to the Fermi Paradox. The idea is this: the universe is like a dark forest at night. You're walking through it, unable to see more than a few feet in any direction. You know there might be others in the forest, but you can't see them, and they can't see you. Now ask yourself, if you heard a sound nearby, would you call out? Would you advertise your location? Or would you stay absolutely silent and hide? The dark forest hypothesis suggests that any civilization that broadcasts its location is taking an enormous risk. You don't know what's out there. You don't know their intentions. You don't know their capabilities. And you can't assess whether they're a threat until it's too late. By the time you detect a hostile civilization, they might already know about you. They might already be on their way. In a universe where resources are finite and competition is inevitable, the safest strategy might be to stay hidden. Civilizations that broadcast their presence get noticed. And civilizations that get noticed might not survive. So everyone stays quiet. Everyone hides. The galaxy fills with civilizations, each one desperately trying not to be detected, each one listening for others, but terrified of what they might hear. This hypothesis suggests that the silence isn't because there's no one out there. It's because everyone is hiding. And if that's true, then our radio broadcasts, our deliberate messages to the stars, our efforts to announce our presence, all of these might be catastrophically naive. We might be children shouting in a forest full of predators. Let's talk about the messages we've sent. In 1974, astronomers used the Arecibo radio telescope in Puerto Rico to beam a message toward the globular star cluster Messier 13. The message was designed by Frank Drake and Carl Sagan. It consisted of 1,679 binary digits arranged in a specific pattern. When decoded, the pattern shows images of the Arecibo telescope itself, a human figure, our solar system, the double helix structure of DNA, and the numbers 1 through 10. The message will take about 25,000 years to reach Messier 13. If anyone there receives it and responds, we won't hear back for another 25,000 years. 50,000 years for a round-trip communication. Civilizations rise and fall in less time. The Pioneer, 10, and 11 spacecraft, launched in 1972 and 1973, each carry a gold-plated aluminum plaque. The plaque shows the figures of a human man and woman, a diagram of our solar system showing Pioneer's origin, and a map showing Earth's location relative to 14 pulsars. Both spacecraft have now left the solar system and are heading into interstellar space. In about 2 million years, Pioneer 10 will pass within a few light years of the star Aldebaran in the constellation Taurus. If anyone there finds it, the plaque will tell them where we are. Voyager 1 and 2, launched in 1977, carry golden records. These 12-inch gold-plated copper discs contain sounds and images selected to portray the diversity of life and culture on Earth. Music from different cultures and eras, greetings in 55 languages, sounds of Earth like thunder, wind, birds, whale songs. Images showing human anatomy, architecture, landscapes, scientific diagrams. The records also include a map showing Earth's location using the same pulsar navigation system as the Pioneer plaques. Voyager 1 is now the most distant human-made object, over 14 billion miles from Earth, and still transmitting data back to us, though it will eventually lose power and go silent. These spacecraft will outlast our civilization. Long after Earth is gone, engulfed by the Sun, in about 5 billion years, when it becomes a red giant, the Voyagers and Pioneers will still be drifting through space. Silent ambassadors carrying evidence that we existed. But if the dark forest hypothesis is correct, these messages might be the most dangerous things humanity has ever created. We've told anyone who finds them exactly where we are. We've provided a map. We've shown our biology, our chemistry, our technological level. And we've done this assuming that whoever finds these messages will be friendly, curious, benevolent. What if that assumption is wrong? There's another explanation for the silence that doesn't require hostile aliens or self-destruction. Maybe civilizations are common, but they don't colonize the galaxy because there's no need to. This is sometimes called the zoo hypothesis. The idea is that advanced civilizations deliberately avoid contact with less developed ones. Like zoologists observing animals in their natural habitat advanced aliens might be watching us while taking care not to interfere. They might have rules, laws, ethical guidelines that prevent them from revealing themselves to civilizations that haven't reached a certain level of development. Earth might be a protected nature preserve, cordoned off and monitored, but left alone. This would explain why we haven't detected anyone. They're deliberately staying hidden. They're here, or at least watching, but they've decided not to make contact. This hypothesis has some appeal because it means we're not alone and we're not in danger. But it raises uncomfortable questions. What criteria would they use to decide when contact is appropriate? Technological advancement? Social maturity? Specific scientific achievements? And what happens when we meet their criteria? Do they suddenly reveal themselves? Do they invite us to join some galactic community? Or have we already failed some test we didn't know we were taking? The zoo hypothesis is comforting in some ways, but it requires us to imagine that all spacefaring civilizations follow the same non-interference policy. If even one civilization didn't follow the rules, if even one decided to make contact or colonize, we should detect them. The fact that we detect nothing suggests either there are no advanced civilizations or they all agree to hide, which seems unlikely. Maybe the answer is simpler. Maybe civilizations are common, but space is just too big. The distances between stars are so enormous that contact is effectively impossible, even if both civilizations survive for millions of years. Let's put this in perspective. The nearest star system to Earth is Alpha Centauri, about 4.24 light-years away, or roughly 25 trillion miles, or 40 trillion kilometers. Light takes 4.24 years to travel that distance. With our current fastest spacecraft, New Horizons, which flew past Pluto, it would take about 78,000 years to reach Alpha Centauri. And that's the nearest star. Most stars are hundreds or thousands of light-years away. A radio signal traveling at light speed would take that long to reach them. A reply would take just as long to come back. You could send a message, and your great-great-great-grandchildren might receive a response. And that's assuming the other civilization is listening on the right frequency at the right time and decides to respond. Physical travel is even more daunting. Even with technology far beyond what we have now, interstellar journeys would take decades or centuries. Generation ships, vessels where multiple generations live and die during the journey, might be possible in theory. But the engineering challenges are immense. You'd need to create a self-sustaining ecosystem, recycle all resources perfectly for centuries, maintain all systems with no possibility of outside help or resupply, and keep a stable society functioning across multiple generations who never set foot on a planet. One mechanical failure could doom everyone. One social breakdown could turn the ship into a drifting tomb. And even if you solved all these problems, you'd arrive at a star system about which you know almost nothing. You might find planets unsuitable for colonization. You might find hazards you didn't anticipate. You might find nothing worth the journey. The galaxy might be filled with civilizations that will never meet because the distances are simply too great to cross. Each one alone, each one sending signals that dissipate into the void, each one wondering if anyone else is out there. Let's consider another possibility that doesn't get discussed as often but is just as unsettling. Maybe we're early. The universe is 13.8 billion years old. That sounds ancient from our perspective. But the universe will continue for trillions of years. stars will keep forming for hundreds of billions of years. The last stars won't burn out until 10 trillion years from now, or more. We exist in the first tiny fraction of cosmic history. Maybe we're among the first civilizations to arise. Maybe in a billion years, the galaxy will be full of life, but right now we're pioneers. We're the first, or among the first. This would explain the silence. There's no one to hear, because everyone else is still evolving, still developing, still centuries or millennia away from radio telescopes and space travel. If that's true, it carries enormous responsibility. What we do now, how we develop, whether we survive, might set the template for everyone who comes after. We might be the first civilization. The decisions we make could echo across billions of years. Here's where things get truly unsettling. What if civilizations don't spread across the galaxy because they discover something that makes expansion pointless or impossible? What if there's knowledge, some fundamental truth about the universe that advanced civilizations inevitably discover, and once they know it, they stop expanding? Maybe they discover that faster-than-light travel is impossible, with no loopholes, no workarounds, and the distances are simply too vast to make expansion worthwhile. Maybe they solve the energy problem and achieve such abundance that physical resources no longer matter, eliminating the motivation for expansion. Maybe they develop virtual reality, so perfect that physical space becomes irrelevant and they retreat into simulated worlds. Maybe they encounter something out there, something dangerous, something that makes staying home the only rational choice. Or maybe they simply go extinct. Not from war or disaster, but from something more subtle. Declining birth rates, loss of purpose, technological stagnation, social collapse. Maybe reaching a certain level of advancement inevitably leads to decline. Maybe civilizations that make it to the stars eventually lose the drive that got them there. They become comfortable, complacent, and eventually they fade away. The universe could be full of civilizations, in various stages of this decline, each one slowly dwindling, none of them expanding. All of them too, absorbed in their own problems to explore. We need to talk about what we've actually seen, because the universe isn't completely featureless. There are things out there we can't explain. Tabby's star, officially designated KIC 8462852, is a star about 1,280 light-years away in the constellation Cygnus. The Kepler Space Telescope monitored this star continuously for years as part of its planet-hunting mission. It detected something bizarre. The star's brightness drops irregularly by up to 22%. That's enormous. When a planet transits in front of a star, the brightness drops by less than 1%. Jupiter, the largest planet in our solar system, would only block about 1% of the sun's light if it passed in front. To block 22% of a star's light, you'd need something truly massive. But it can't be a planet. The dimming pattern is irregular, not periodic like you'd expect from an orbiting planet. And the dimming events last for different lengths of time. One explanation that got significant attention was that we might be seeing a megastructure, something built by an advanced civilization. Specifically, a Dyson swarm, a collection of solar collectors orbiting a star to capture its energy output. A civilization advanced enough to build such a structure would have energy resources beyond our imagination. They could power their entire civilization with the star's output. But as more data came in, the megastructure hypothesis became less likely. The star shows other unusual characteristics that suggest natural phenomena. The leading explanation now is that we're seeing the aftermath of a planetary collision or a swarm of comets, though neither explanation fully accounts for all the observations. We still don't know what's causing the dimming of Tabby's star. But the fact that our first instinct was to wonder if we were seeing alien technology tells you something about our expectations. We're looking for signs of intelligence. And when we find something we can't explain, we wonder. Oumuamua is another mystery. In October 2017, astronomers detected an object passing through our solar system. This was already unusual because the object's trajectory showed it came from interstellar space. It wasn't orbiting the sun. It was passing through. Detailed observations revealed that Oumuamua was accelerating slightly as it moved away from the sun, faster than could be explained by the sun's gravity alone. Objects normally slow down as they move away from the sun. Oumuamua was speeding up. For a comet, this would make sense. Comets accelerate when sunlight vaporizes ice on their surface, creating jets of gas that act like tiny rocket engines. But Oumuamua showed no signs of outgassing, no tail, no coma, nothing that would indicate it was a comet. Its acceleration remained unexplained. Its shape was also unusual. Based on how its brightness varied as it tumbled through space, astronomers calculated that Oumuamua was extremely elongated, shaped like a cigar or perhaps a pancake, with dimensions roughly 330 feet by 33 feet. Nothing in our solar system looks like that. Natural objects tend to be roughly spherical, or at least not so extremely elongated. Some scientists, including Harvard astronomer Avi Loeb, suggested that Oumuamua might be artificial. Specifically, a light sail, a thin reflective sheet designed to catch starlight for propulsion. This would explain the unusual shape and the acceleration. A light sail pushed by sunlight would accelerate exactly as Oumuamua did. Most astronomers disagreed, arguing that there were natural explanations, even if we didn't fully understand them. Maybe Oumuamua was made of unusual materials. Maybe it was outgassing hydrogen that we couldn't detect. Maybe its shape was the result of some formation process we haven't seen before. But we'll never know for certain because Oumuamua is gone. It's already left our solar system and is heading back into interstellar space. We'll never get another look at it. And that uncertainty, that inability to definitively rule out the artificial hypothesis, bothers people. Because if Oumuamua was a probe, if it was sent here deliberately to observe our solar system, then someone knows we're here. And they haven't said hello. The silence might also be temporary. Radio astronomy is only about 70 years old. The first radio telescopes were built in the 1950s. SETI has been operating for about 60 years. That's an incredibly short time on cosmic scales. Maybe we've been listening, but we haven't been listening long enough. Maybe the galaxy is full of civilizations, but they broadcast rarely. Maybe they send a signal every 10,000 years, and we've been listening during a quiet period. Or maybe civilizations go through phases. They broadcast for a while when they first develop radio technology. Then they switch to other methods of communication that we can't detect. Laser communication, neutrino beams, quantum entanglement, technologies we haven't even imagined. Radio might be like smoke signals, something you use when you're primitive, but abandon once you develop better methods. If that's true, then the window where a civilization broadcasts detectable radio signals might be brief. A few centuries at most. And if we're not listening during that window, we miss them. This would explain the silence. Not because there's no one out there, but because we're using outdated technology to search for signals that advanced civilizations stopped sending thousands of years ago. We're listening for smoke signals in an age of fiber optics. One of the most disturbing possibilities is that intelligence itself might be a dead end. Maybe intelligence is an evolutionary accident that looks like an advantage in the short term, but turns out to be fatal in the long term. Think about it this way. For billions of years, life on Earth got along fine, without intelligence. Single-celled organisms dominated for 3 billion years. Complex life has existed for only about 600 million years. Intelligence, human-level intelligence, has existed for maybe 200,000 years. Technological civilization has existed for only about 10,000 years. In evolutionary terms, intelligence is brand new. We don't yet know if it's sustainable. Intelligence gives us power, but it doesn't necessarily give us wisdom. We can split atoms, but we might use that knowledge to build weapons that destroy us. We can engineer organisms, but we might create pathogens that wipe us out. We can build artificial intelligence, but we might lose control of it. We can change our planet's climate, but we might make it uninhabitable. Every advantage intelligence provides comes with risks that could destroy us. And we've only had these capabilities for a few decades. We haven't proven we can handle them responsibly over the long term. Maybe no one can. Maybe every intelligent species eventually develops technology that exceeds its wisdom, and that technology inevitably destroys them. The galaxy might be full of planets where intelligence arose, flourished briefly, then went extinct, leaving behind ruins and silence. This possibility is particularly chilling because it means the silence isn't a mystery to be solved. It's a warning. It's the universe telling us that intelligence doesn't guarantee survival. It might even make extinction more likely. Let's talk about the Kardashev scale, because it helps us think about what advanced civilizations might look like. The scale was proposed by Soviet astronomer Nikolai Kardashev in 1964. It classifies civilizations based on their energy consumption. A Type 1 civilization can harness all the energy available on its planet. This includes solar energy hitting the planet, geothermal energy, tidal energy, everything. A Type 1 civilization has complete control over its planet's resources and weather. Humanity isn't there yet. We're currently around 0.7 on the Kardashev scale. We use a fraction of Earth's available energy. We're moving toward Type 1, but we haven't reached it. A Type 2 civilization can harness all the energy output of its star. This is where Dyson spheres and Dyson swarms come in. You surround your star with collectors that capture its energy output. The Sun produces about 3.8 times 10 to the 26th watts of power. A Type 2 civilization would have access to all of that. With that much energy, you could do things we can barely imagine. Move planets, terraform worlds, travel between stars, run computational systems the size of solar systems. A Type 3 civilization can harness the energy output of an entire galaxy. This would require technology so advanced it looks like magic to us. You'd control billions of stars, countless planets. You'd engineer on galactic scales. Now, here's the thing. A Type 2 or Type 3 civilization should be detectable. A Dyson sphere would be visible from light years away as an infrared source. A star putting out heat but very little visible light because the collectors are absorbing the light and re-radiating it as heat. A Type 3 civilization engineering across an entire galaxy would produce signatures we couldn't miss. Altered stellar spectra, unusual infrared emissions, patterns that couldn't occur naturally. Astronomers have looked for these signatures. They've surveyed hundreds of thousands of galaxies, looking for the telltale signs of Type 3 civilizations. They've examined stars, looking for Dyson sphere candidates. They've found nothing. No. Type 3 civilizations. No. Type 2 civilizations. As far as we can tell, no one has reached those levels. This is strange, because if civilizations commonly survive and advance, some should have reached Type 2 or Type 3 by now. The fact that we see no evidence of advanced civilizations suggests either they don't exist, they're extremely rare, or they don't advance to those levels. Maybe there's a barrier. Maybe civilizations reach a certain point and stop advancing. Or maybe they destroy themselves before reaching Type 2. The simulation hypothesis offers another explanation for the silence. This hypothesis suggests that our reality might be a computer simulation. If that's true, then the universe might be silent because whoever created the simulation didn't populate it with other civilizations. Or maybe they did, but they're not simulating them in detail unless we interact with them. Like video game, non-player characters that only become active when the player approaches. This sounds like science fiction, but some serious scientists and philosophers take it seriously. The argument goes like this. If it's possible to create realistic simulations of conscious beings, then any sufficiently advanced civilization would probably create many such simulations. If that's true, then there are likely far more simulated realities than base reality. Which means, statistically, you're more likely to be in a simulation than in the original universe. If we're in a simulation, the Fermi Paradox disappears. There are no aliens because the simulation creators didn't include them. The universe is silent because it's not real. We're the only conscious beings in the simulation, and everything else is backdrop. This hypothesis is unfalsifiable, which makes it philosophically problematic. You can't prove you're not in a simulation. Any evidence you find could be part of the simulation. But it's an explanation for the silence that doesn't require extinction or dark forests or rare Earth scenarios. Here's something we need to consider. Maybe we're wrong about what signs of intelligence look like. We're looking for radio signals, megastructures, signs of engineering. But we're basing this on what we would do, how we would develop. An alien civilization might be so different from us that we wouldn't recognize their technology even if we were looking right at it. They might communicate in ways we haven't imagined. They might use energy sources we don't understand. They might build structures that look natural to us because we don't know what to look for. Consider that we've only known about radio waves for about 130 years. Before James Clerk Maxwell developed his equations of electromagnetism in the 1860s, humans had no idea radio waves existed. They were passing through us, through Earth, through everything, and we were completely unaware. What if there are other phenomena, other types of radiation, other ways to transmit information that we haven't discovered yet? What if advanced civilizations use those methods and we're still looking for smoke signals? We might be deaf to their transmissions, not because they're not transmitting, but because we don't have the right receivers. We don't even know what we're missing. The Great Filter hypothesis deserves deeper examination because it's one of the most important ideas in thinking about the Fermi Paradox. The concept is simple but profound. Somewhere between non-living matter and galaxy-spanning civilizations, there's a step that's extremely unlikely. So unlikely that it acts as a filter, removing almost everyone from the process. The question is, where is that filter? If the filter is in our past, that's good news. It means we've already overcome the hard part. Maybe the origin of life is incredibly difficult. Maybe the jump from single-celled organisms to complex life is almost impossible. Maybe the evolution of intelligence is a 1 in a billion fluke. If any of these are true, we might be alone, or nearly alone, in the universe. But we've survived the filter. We've made it through. Our future is potentially limitless. But if the filter is ahead of us, that's terrifying. It means something awaits every civilization, something that almost no one survives. And we haven't reached it yet. Think about the things that could destroy us. Nuclear war. We have enough nuclear weapons to render Earth uninhabitable. The bombs dropped on Hiroshima and Nagasaki in 1945 were tiny compared to modern thermonuclear weapons. A full-scale nuclear exchange would create firestorms, massive clouds of smoke and ash that would block sunlight for years, creating a nuclear winter that would collapse agriculture and starve billions. Biological weapons. We're getting better at genetic engineering. We can now edit genomes with CRISPR technology, inserting, deleting, or modifying genes with precision. This could cure diseases. It could also create engineered pathogens more deadly than anything nature has produced. A weaponized virus or bacteria, designed to spread rapidly and resist all treatments, could end civilization. Artificial intelligence. We're developing AI systems that learn and improve themselves. At some point, we might create an AI that's smarter than humans. Once that happens, we might lose control. An AI with goals misaligned with human survival could see us as obstacles or resources. It might decide the most efficient way to achieve its goals involves getting rid of us. Nanotechnology. Molecular manufacturing could give us incredible power over matter. It could also go catastrophically wrong. Self-replicating nanobots could multiply out of control, consuming resources faster than we can stop them. The grey goo scenario, where self-replicating machines reduce everything to copies of themselves. Climate change. We're altering our planet's climate faster than at any time in human history, except for major asteroid impacts. If we push the system too far, we could trigger runaway effects. Melting permafrost releases methane, a potent greenhouse gas which causes more warming, which melts more permafrost. Ocean currents could change, rainfall patterns could shift, agriculture could collapse. Any of these could be the great filter. And here's the terrifying part. We might have already started down one of these paths. We might be in the middle of our filter right now without realizing it. Maybe the silence of the universe isn't a mystery. Maybe it's evidence. Evidence that civilizations reach this point, develop these technologies, and then fail. Every time. The universe is silent because no one makes it through. Let's consider the timescales involved, because they're important. Earth formed about 4.54 billion years ago. Life appeared relatively quickly, within a few 100 million years after Earth's surface cooled enough to allow liquid water. But that life remained simple for an incredibly long time. Single-celled organisms dominated for about 3 billion years. Complex life, multicellular organisms, only appeared about 600 million years ago. The Cambrian explosion, when most modern animal body plans appeared, happened about 540 million years ago. Fish appeared about 500 million years ago. Land plants, about 470 million years ago. Insects, about 400 million years ago. Reptiles, about 312 million years ago. Dinosaurs ruled for about 165 million years, from roughly 230 million years ago until their extinction 66 million years ago. Mammals were around during the dinosaur era, but remained small and insignificant. Only after the dinosaurs disappeared did mammals diversify and grow larger. Primates appeared about 55 million years ago. The first apes, about 25 million years ago. The human lineage split from chimpanzees about 6 to 7 million years ago. Our genus, Homo, appeared about 2.8 million years ago. Anatomically modern humans, Homo sapiens, appeared about 300,000 years ago. For most of that time, we lived as hunter-gatherers. Agriculture was invented only about 10,000 years ago. Writing about 5,000 years ago. The Industrial Revolution about 250 years ago. Radio communication about 130 years ago. Nuclear weapons about 80 years ago. The internet about 50 years ago. Widely available only about 30 years ago. Look at that timeline. Life appeared quickly. Intelligence took billions of years. Technology developed in the blink of an eye. We went from agriculture to nuclear weapons in 10,000 years. We went from the first radio transmission to artificial intelligence in 130 years. The technological phase, the phase where we have the power to destroy ourselves or spread to the stars, is incredibly brief compared to the time it took to get here. Maybe that's the filter. Maybe civilizations reach this point and almost always destroy themselves before they can expand. The window where you have both the technology to colonize other worlds and the wisdom not to destroy yourself might be very narrow. Maybe most civilizations don't make it through that window. Here's something else to consider. We talk about advanced civilizations, but we're making assumptions about what advancement means. We assume advancement means expansion, growth, spreading across the galaxy, but maybe advanced civilizations don't do that. Maybe they turn inward instead. If you can create perfect virtual realities, why would you bother with physical space? Space is dangerous, expensive, difficult to traverse. Virtual realities are safe, cheap, infinitely customizable. You could create any world you want, live any life you imagine. You could upload your consciousness, become immortal in a digital realm. Physical reality might become irrelevant. An advanced civilization might retreat into computational substrates, using their star's energy to run simulations of unimaginable complexity. From the outside, they'd be invisible. Just a star with some unusual infrared characteristics, maybe not even that if they're efficient. The galaxy could be full of civilizations living in virtual worlds, indifferent to physical space, uninterested in expansion. They're out there, but they're not doing anything we'd recognize as expansion or communication. They're focused entirely inward. The anthropic principle offers another perspective. This principle states that we observe the universe as we do, because if it were different, we wouldn't be here to observe it. Applied to the Fermi Paradox, it suggests that we find ourselves in a universe that appears empty, because if the universe were full of aggressive civilizations, we wouldn't have survived long enough to wonder about it. We exist in a universe where intelligent life is rare or well-hidden, or non-expansionist, because those are the only types of universes where species like us can arise and persist long enough to develop technology and ask questions. In universes filled with aggressive civilizations, planets like Earth get colonized or destroyed before native intelligence evolves. We don't see aliens because we exist in a timeline, a branch of reality, where they're absent or distant enough to have left us alone. This doesn't solve the Fermi Paradox so much as reframe it. It's not, where is everyone? It's, why do we find ourselves in a universe where everyone appears absent? And the answer might be that we couldn't exist in any other kind of universe. Let's talk about what we should do with all this uncertainty. Should we keep broadcasting our presence? Should we deliberately send messages to the stars? Or should we stay quiet? This is an active debate among scientists. Some argue that we should be shouting as loud as we can. Send powerful radio signals, laser pulses, messages describing who we are and where we live. They argue that the benefits of potential contact outweigh the risks. Any civilization advanced enough to reach us would likely be peaceful, or at least rational enough, to recognize that cooperation is better than conflict. And if there's danger, staying quiet won't help. Any civilization advanced enough to be a threat is probably advanced enough to detect us, whether we broadcast or not. They could spot our atmospheric composition, the chemical signatures of industrial civilization. They could detect our artificial lights on the night side of the planet. They could intercept our radio and television broadcasts that have been leaking into space for a century. Hiding is futile, so we might as well reach out. Others argue that we should be extremely cautious. We don't know what's out there. Broadcasting our location is irreversible. Once the message is sent, we can't take it back. It spreads outward at light speed forever. If there are hostile civilizations, we've just told them where we are. They point to the dark forest hypothesis and argue that the universe's silence might be a warning. Everyone else is hiding. We should too. Better to listen than to broadcast. Better to gather information before revealing ourselves. We have time. We can keep improving our detection technology. Keep listening. Keep searching. Eventually, we'll either detect others or become confident that we're alone. But rushing to broadcast now is reckless. This debate has real implications. There are organizations that have sent deliberate messages to stars. In 2008, NASA beamed the Beatles' song Across the Universe toward the star Polaris, 430 light-years away. In 2017, a group called Messaging, Extraterrestrial Intelligence, sent a message toward a star system with a potentially habitable planet, arriving in 2033. These actions are controversial because they're made by small groups without global consensus. They're making decisions that affect all of humanity, potentially all future humans, without asking permission. Should that be allowed? Should there be international agreements about broadcasting to space? Some scientists think yes. They've called for a global moratorium on deliberate transmissions until we can have a broader discussion about the risks and benefits. Others think regulation is impossible and undesirable. Anyone with a powerful enough radio transmitter can send messages. You can't police everyone. And who gets to decide? Which government? Which organization? These are hard questions with no clear answers. The silence of the universe forces us to confront our assumptions about our place in the cosmos. For most of human history, we thought we were the center of everything. Earth was the center of the universe. The sun and planets revolved around us. We were special, chosen, unique. Then Copernicus showed us that Earth orbits the sun. Then we discovered that the sun is just one of billions of stars in our galaxy. Then we discovered that our galaxy is just one of trillions of galaxies. Each discovery pushed us further from the center. We became less special, more ordinary. Just one planet among trillions. The Copernican principle suggests that we're not special. We're typical. If Earth is ordinary, then life should be common. Intelligence should be common. Technological civilizations should be common. But the universe is silent. Either we're wrong about being ordinary, or something else is going on. Maybe we're not as ordinary as we think. Maybe Earth is special in ways we don't appreciate. Maybe the combination of factors that allowed complex life to evolve here is rare. Or maybe we are ordinary, and the silence tells us what awaits ordinary civilizations. They arise, they develop, they face challenges, and they fail. We're ordinary, which means we'll probably fail too. The silence becomes a prediction of our future. One possibility that doesn't get mentioned often enough is that we might be asking the wrong questions. The Fermi Paradox assumes that civilizations want to expand, communicate, make their presence known. But maybe they don't. Maybe the drive to explore and expand is a phase civilizations go through and then leave behind. Young civilizations explore because they're curious, because they need resources, because they haven't learned better. Mature civilizations might realize that expansion is pointless. They might achieve post-scarcity economics, where resources are no longer scarce. They might develop technology that lets them create anything they need from basic elements. They might solve the energy problem with fusion or matter, antimatter annihilation. Once you have unlimited energy and can create any material you need, why expand? Why build colonies on other worlds when you can build habitats in space or underground or in virtual reality? Why travel to other stars when you have everything you need at home? Maybe the galaxy is full of civilizations that went through an expansionist phase and then settled down. They're out there, but they're content. They're not broadcasting because they're not looking for contact. They're not building megastructures because they don't need to. They're living quietly on their home worlds or in their home systems, and from the outside, they look like nothing at all. Just ordinary stars with ordinary planets. The more we learn, the stranger the silence becomes. We've discovered thousands of exoplanets. We know rocky planets are common. We know planets in the habitable zone are common. We've found organic molecules in interstellar space, in comets, in meteorites. The building blocks of life are everywhere. We've found liquid water on Mars, under the ice of Europa and Enceladus. We've found complex organic chemistry on Titan. Everything we learn suggests that the ingredients for life are common, that habitable environments are common, that the universe should be teeming with life. But we see no evidence of it. No biosignatures in exoplanet atmospheres. No radio signals. No megastructures. No signs of intelligence anywhere except Earth. The disconnect between what we expect and what we observe keeps growing. Either our expectations are wrong, or we're missing something fundamental. Let's talk about what happens if we do make contact. Suppose tomorrow we detect a signal, a clear, unambiguous, artificial radio transmission from a star system 50 light-years away. It's repeating. It's modulated. It's unmistakably intelligent in origin. What do? First, we verify. Multiple telescopes, multiple observers, confirm the signal. Make absolutely certain it's real, and not interference, not a hoax, not a misidentification. Then, assuming it's real, we analyze. What's the signal saying? Is it a message? Is it just leakage, their equivalent of our radio broadcasts? Does it contain information we can decode? If it's a message, do we respond? This is where things get complicated. The signal took 50 years to reach us. Our response would take 50 years to reach them. That's a 100-year round trip. The people who detect our response won't be the people who sent the original signal. It would be their grandchildren or great-grandchildren. How do you have a conversation across those timescales? And should we respond at all? Some people would say, absolutely, yes. This is first contact. This is one of the most important moments in human history. We have to respond. Others would say, absolutely not. We don't know who they are. We don't know their intentions. Responding tells them we're here and confirms we received their message. That's information we can't take back. The decision about whether to respond would trigger massive debate. Governments would get involved. The United Nations would convene. Scientific organizations would issue statements. Religious leaders would weigh in. Everyone would have an opinion. And there's no established protocol, no agreed-upon process for making this decision. We'd be making it up as we went along. The political implications would be staggering. Who speaks for Earth? Which country? Which organization? What do we say? How do we decide what information to share? Do we tell them about our wars, our problems, our divisions? Or do we present a united front, a sanitized version of humanity? And what would the psychological impact be? Knowing that we're not alone would fundamentally change how humanity sees itself. Every religion would have to grapple with the implications. Every philosophy would need to be reconsidered. We'd no longer be the only intelligent species. That would change everything. The universe's silence might be the answer to a question we haven't asked yet. Maybe we're thinking about this wrong. Maybe the question isn't, where is everyone? Maybe the question is, what is intelligence for? We assume intelligence is advantageous. It helped us survive, build civilizations, develop technology. But what if intelligence is just one strategy among many, and not necessarily the best one? Bacteria have existed for over 3 billion years. They've survived mass extinctions that wiped out more complex life. They'll probably outlast us. They've conquered every environment on Earth, from deep-sea vents to Antarctic ice to radioactive waste pools. They don't need intelligence. They just need to reproduce and adapt. Maybe intelligence is a costly adaptation that works in the short term but fails in the long term. It requires enormous energy. The human brain uses about 20% of our caloric intake. It requires long childhoods, extended periods of vulnerability while young brains develop. It requires social structures to pass knowledge between generations. All of this is expensive. And what does it get you? The ability to modify your environment. But modifying your environment can backfire. We've modified Earth's atmosphere, oceans, climate. We've created weapons that can end civilization. We've developed technologies we might not be able to control. Maybe intelligence is a trap. It feels like an advantage. It is an advantage for a while. But eventually, it gives you enough power to destroy yourself. And most species don't survive that. The universe is silent because intelligence doesn't survive. Not because it's rare, but because it's self-terminating. Here's the most unsettling possibility of all. Maybe we have detected aliens and we just don't know it. Our datasets are enormous. The Kepler telescope alone collected data on over 500,000 stars. SETI programs have scanned millions of frequencies from thousands of stars. We have radio telescope data going back decades. Most of it has never been fully analyzed. We use algorithms to search for specific patterns, but algorithms can only find what they're designed to find. If the signal doesn't match our expectations, if it's too complex or too simple, or uses modulation we're not looking for, we might miss it. It could be sitting in archived data, waiting for someone to notice it. Or maybe we have noticed anomalies, but dismissed them. Science is conservative. Extraordinary claims require extraordinary evidence. If you find something weird in your data, your first assumption is that it's an error, a glitch, interference, something mundane. You don't jump to aliens. You investigate other possibilities first. And if you can't definitively rule out natural explanations, you don't publish. You don't claim you've found aliens based on ambiguous evidence. So, maybe there are signals out there. Weak signals, strange signals, things that don't quite fit. But they're not strong enough, not clear enough, not unambiguous enough to overcome the scientific community's skepticism. They're filed away, noted but not pursued. And we keep searching. The silence of the universe might be telling us something profound about the nature of existence. Maybe consciousness, intelligence, civilization, all of these are temporary phenomena, brief flickers in the cosmic dark. They arise, they exist for a moment, and they disappear. The universe is mostly empty space, mostly hydrogen and helium, mostly simple. Complexity is rare and fragile. We're a rare occurrence, a temporary organization of matter into something that can think and wonder. But matter doesn't stay organized. Entropy increases. Things fall apart. Civilizations rise and fall. Stars burn out. Galaxies disperse. Eventually, in the far future, the universe will be cold and dark. All stars will have burned out. All black holes will have evaporated. Nothing will remain but photons and elementary particles spreading farther and farther apart. In that context, our existence is miraculous. Against all odds, in a tiny window of time when stars still shine and planets still exist, matter organized itself into creatures that can understand the universe. We exist. We're here. We can look up at the stars and wonder. The fact that we appear to be alone doesn't diminish that. If anything, it makes it more precious. We might be the only ones. The only consciousness in the observable universe. The only way the universe has to understand itself. That's a staggering responsibility. The silence forces us to make a choice. We can interpret it as threatening. Everyone out there is hiding, and we should too. The universe is a dangerous place, and revealing ourselves is suicide. Or we can interpret it as hopeful. We're among the first. We're pioneers. What we do matters because we might be setting an example for everyone who comes after. Or we can interpret it as lonely. We're alone, truly alone. There's no one out there to meet, to learn from, to share the universe with. We're on our own. Each interpretation leads to different conclusions about what we should do. If the universe is dangerous, we should develop defensive technologies, stay hidden, focus on survival. If we're pioneers, we should expand, explore, establish ourselves on other worlds so that one disaster can't end us. If we're alone, we should cherish what we have, protect Earth, recognize that this might be the only place where life exists. The truth is, we don't know which interpretation is correct. We might never know. The universe keeps its secrets. What we do know is that the silence is real. We've been listening for 60 years. We've examined thousands of star systems. We've looked for megastructures, biosignatures, radio signals, optical signals, anything that might indicate intelligence. We've found nothing. The universe, as far as we can tell, is empty. Or at least empty of anyone who wants to be found. That absence, that silence, is one of the deepest mysteries we've ever encountered. It touches on questions of existence, purpose, destiny. It forces us to confront the possibility that we might be alone. Really, truly alone in a universe vast beyond comprehension. Or it forces us to confront the possibility that everyone else has learned something we haven't. They've learned to stay quiet. They've learned that silence is survival. And we're the naive ones, broadcasting our location, announcing our presence, unaware of the danger. The universe is silent. That's a fact. Why it's silent, what that silence means, what we should do about it, these are questions we're still trying to answer. Every new discovery, every new exoplanet, every new piece of data adds to our understanding, but doesn't resolve the central mystery. We keep looking. We keep listening. We keep hoping that one day we'll detect something. A signal, a sign, proof that we're not alone. But until that day comes, we live with the silence. And we wonder what it means. Is it a warning? Is it a puzzle? Is it just the way things are in a universe where intelligence is vanishingly rare? We don't know. But we keep searching, because the question is too important to ignore, because the implications are too profound to dismiss, because knowing whether we're alone might be the most important thing humanity ever discovers. The silence of the universe changes everything. It challenges our assumptions about life, intelligence, our future. It forces us to question whether we're special or ordinary, whether we're alone or just early, whether we're safe or in danger. And until we break that silence, until we make contact or become absolutely certain that there's no one to contact, we won't know. We'll keep wondering. We'll keep searching. We'll keep listening to the cosmic void, hoping for an answer. But for now, the universe remains silent. And that silence might be the most important message we'll ever receive. We need to examine the actual science of detecting alien civilizations, because the methods we're using have limitations that might explain the silence. Radio SETI, the most famous approach, searches for narrowband signals. Natural cosmic sources produce broadband radio emissions spread across a wide range of frequencies. An artificial transmitter would produce a signal concentrated at a specific frequency. That concentration makes it distinguishable from background noise. But here's the problem. The radio spectrum is enormous. Frequencies from a few megahertz to hundreds of gigahertz could potentially be used for communication. That's billions of possible channels. We can't monitor all of them simultaneously. We have to choose which frequencies to search. We've focused on frequencies where Earth's atmosphere is relatively transparent and where cosmic background noise is relatively low. The water hole, frequencies between 1320 and 1660 MHz, between the emission lines of hydrogen and hydroxyl, is considered a logical place to search. If aliens think the same way we do, they might broadcast there. But that's an assumption. Maybe they use different frequencies. Maybe they use methods of communication we haven't imagined. Optical SETI searches for laser pulses. A powerful laser pulse directed at Earth would briefly outshine the star it's coming from. These pulses would be incredibly brief, microseconds or nanoseconds, but extremely bright. If you're pointing your telescope at the right star at the right moment, you'd detect it. But the galaxy contains hundreds of billions of stars. The chances of looking at the right star at the exact microsecond when a laser pulse arrives are vanishingly small. It's like trying to see a camera flash on the other side of a city while you're randomly glancing in different directions. Even if it happens, you'll probably miss it. Technosignatures offer another approach. Instead of looking for deliberate messages, we look for the byproducts of advanced technology. Industrial pollution in an exoplanet's atmosphere. The chemical signatures of artificial compounds that don't occur naturally. Heat signatures from Dyson spheres or other megastructures. Unusual light curves from stars where something massive is orbiting. City lights on the night side of exoplanets. Large-scale engineering projects that alter the light from a star. This approach doesn't require aliens to want to communicate. It just requires them to exist and use technology. But detecting these signatures requires capabilities we're only beginning to develop. We need better telescopes, better spectroscopy, better data analysis. The James Webb Space Telescope can analyze exoplanet atmospheres in unprecedented detail. Future telescopes will be even more capable. Maybe we'll detect biosignatures or technosignatures in the next few decades. Or maybe we won't. Maybe civilizations are careful enough not to leave detectable traces. Maybe they're efficient enough that their technology doesn't produce waste heat or pollution. Maybe they're advanced enough to clean up after themselves. The Drake equation is the famous attempt to estimate how many communicating civilizations exist in our galaxy. Frank Drake formulated it in 1961 as a way to organize thinking about the problem. The equation multiplies several factors together. The rate of star formation in our galaxy, the fraction of stars that have planets, the number of planets per star that could support life, the fraction of those planets where life actually arises, the fraction of life-bearing planets where intelligence evolves, the fraction of intelligent species that develop technology capable of communication, and the length of time such civilizations broadcast detectable signals. Plug in numbers for each factor, and you get an estimate of how many communicating civilizations exist right now. The problem is that we don't know most of these numbers. The first few factors we can estimate. We know the star formation rate. We know most stars have planets. We're starting to understand how common potentially habitable planets are. But the later factors, the probability of life arising, the probability of intelligence evolving, the probability of technology developing, the lifetime of civilizations, we have no data except Earth. And a sample size of 1 tells you almost nothing. You can plug in optimistic numbers and get millions of civilizations. You can plug in pessimistic numbers and get less than 1, meaning we're alone. The equation doesn't give us an answer. It gives us a framework for organizing our ignorance. We know what we don't know. The Drake equation has been criticized as useless because it has so many unknown parameters. But that criticism misses the point. The equation isn't meant to give a precise answer. It's meant to show us what questions we need to answer. As we learn more, we can refine the estimates. We now know that planets are common. That updates one factor. We're learning about the chemistry of exoplanet atmospheres. That will help us understand how common the right conditions for life might be. We're studying the origin of life on Earth. Every breakthrough there helps us estimate how likely life is to arise elsewhere. Slowly, over decades or centuries, we'll replace speculation with data. The equation will become more useful as our knowledge grows. But right now, it mostly tells us that we don't know enough to say whether we're alone. Let's consider the economics of interstellar colonization, because this might explain why no one has spread across the galaxy. Establishing a colony on another planet is enormously expensive. You need to transport people, equipment, supplies across light years of space. The journey takes decades or centuries with any plausible propulsion system. Once you arrive, you need to establish life support, build habitats, extract resources, become self-sufficient. All of this requires massive investment with no guarantee of return. On Earth, colonization was driven by economics. Colonies provided resources, trade goods, new markets. They were expensive to establish, but potentially profitable. But interstellar colonies can't trade with the home world. The distances are too vast. Communication takes years. Physical transport takes centuries. You can't ship raw materials back to Earth. You can't sell products to other star systems. Each colony would be economically isolated. So, what's the motivation? Idealism, the desire to spread humanity, to ensure our survival by establishing redundant populations. Scientific curiosity, the desire to explore and study new worlds. Religious or ideological goals, establishing utopian societies away from Earth. Escape, leaving behind overcrowding, pollution, political problems, persecution. These motivations might be enough for some people, enough to establish a few colonies. But they're unlikely to drive the massive expansion that would fill the galaxy. That would require millions of colonies, each requiring enormous investment. Where does that investment come from? Who pays for it? If there's no economic return, if each colony is a permanent drain on resources, then expansion slows and eventually stops. Maybe civilizations establish a few nearby colonies and then plateau. They spread to their nearest neighbors, dozens or hundreds of light years away, and then stop. That would explain the silence. There are civilizations out there, but they're clustered around their home stars. They haven't filled the galaxy, because filling the galaxy doesn't make economic sense. We should talk about the physical challenges of interstellar travel because they're more severe than most people realize. Space is not empty. Even interstellar space contains gas and dust, incredibly diffuse, but not absent. Typical density in interstellar space is about 1 atom per cubic centimeter. That doesn't sound like much. But when you're traveling at a significant fraction of light speed, even sparse gas becomes a problem. Impact with gas atoms at high speed generates heat and radiation. The faster you go, the worse it gets. At 10% of light speed, collisions with interstellar hydrogen create enough radiation to sterilize anything biological and damage electronics. You'd need heavy shielding, which adds mass, which requires more energy to accelerate. At higher speeds, the problem becomes worse. At 90% of light speed, impacting a single grain of dust releases energy equivalent to a hand grenade. The hydrogen gas itself becomes high-energy radiation from the spacecraft's reference frame. You'd need several feet of shielding, magnetic fields to deflect charged particles, active systems to vaporize dust grains before they hit. All of this adds mass and complexity. Then there's the energy requirement. Accelerating a spacecraft to a significant fraction of light speed requires enormous energy. To accelerate 1,000 kilograms, about the mass of a small car, to 10% of light speed requires about 4.5 times 10 to the 18th joules. That's roughly the total energy output of the United States for an entire year. And that's just to accelerate. You also need to decelerate when you arrive, which requires the same amount of energy. So, double the number. And you probably want to carry more than 1,000 kilograms. You need life support, scientific instruments, communication equipment, supplies, people, if it's a crewed mission. A realistic interstellar spacecraft might mass hundreds of tons or more. The energy requirements scale linearly with mass. Where does that energy come from? Conventional rockets won't work. The fuel would be too massive. You'd need something like a fusion drive, a matter-antimatter engine, or a laser sail pushed by enormous laser arrays in the home system. All of these are theoretical. We haven't built any of them. We don't know if they're practical. Even if we solve the propulsion problem, there's the time problem. At 10% of light speed, the nearest star is 42 years away. Practical interstellar missions might travel slower, maybe 5% of light speed. That's 84 years to the nearest star. You'd need a generation ship for a crewed mission. Or suspended animation, if that's possible. Or you send robots and accept that no one who launches the mission will see the results. These challenges might be solvable with sufficient technological advancement. But they're severe enough that it's not obvious. Interstellar travel is practical, even for advanced civilizations. Maybe everyone who tries concludes it's too difficult, too expensive, too dangerous. Maybe that's why the galaxy isn't colonized. Not because civilizations don't exist, but because interstellar travel is prohibitively hard. The notion of time in cosmic contexts changes how we should think about the Fermi Paradox. Humans have been broadcasting radio signals for about 100 years. That's how long we've been detectable to anyone listening. 100 years out of 13.8 billion years of cosmic history. That's 0.0000007% of the universe's age. We've existed as a technological civilization for a cosmic eye blink. Now, imagine an alien civilization 1,000 light years away. They're also broadcasting, but they went through their radio era 2,000 years ago. By the time their signals reach us, they've moved on to other technologies. We're not listening at the right time. Or they're going through their radio era right now, but we're 1,000 light years away. Their signals won't reach us for another 1,000 years. By the time we hear them, we might have moved on to other technologies too. The window of overlap, the time when two civilizations are both detectable to each other, might be very brief. A few centuries at most. In a galaxy 100,000 light years across, the chances of two civilizations being in detectable phases and close enough and oriented correctly to detect each other might be vanishingly small. It's not that civilizations don't exist. It's that we keep missing each other in time. Let's explore the concept of Dyson spheres more deeply, because they're central to thinking about advanced civilizations. Freeman Dyson proposed in 1960 that a sufficiently advanced civilization would eventually surround its star with solar collectors to capture most or all of its energy output. Not a solid shell, that's structurally impossible, but a swarm of orbiting collectors, millions or billions of individual platforms. A Dyson swarm would be the ultimate expression of a Type 2 civilization. You'd have access to the full energy output of your star. For our Sun, that's about 3.8 times 10 to the 26th watts. That's about 2 billion times the total power consumption of current human civilization. With that much energy, you could do almost anything. Run computational systems larger than planets. Manipulate matter on enormous scales. Power civilizations of trillions of beings. Even begin to move your star, using asymmetric radiation pressure to alter its trajectory over millions of years. But a Dyson swarm would be visible from light years away. The star's visible light would be blocked or reduced. The swarm would re-radiate the captured energy as infrared radiation. You'd see a star that's dim in visible light but bright in infrared. That's a distinctive signature that wouldn't occur naturally. Astronomers have looked for such signatures. They've examined stars with unusual infrared excess, stars that are brighter in infrared than expected based on their visible light. Most of these have natural explanations. Dust clouds around young stars absorb visible light and re-radiate it as infrared. Asteroid collisions create temporary dust clouds. But in a few cases, the infrared excess is harder to explain. Tabby's star is the most famous example. Its irregular dimming and strange infrared signature don't fit any simple natural model. Most astronomers think the explanation will turn out to be natural, some combination of dust and comets and orbital dynamics we don't fully understand. But we don't know for certain. The possibility that we're seeing a partial Dyson swarm, a work in progress, can't be completely ruled out. Beyond individual stars, astronomers have looked at entire galaxies. A Type 3 civilization would engineer on galactic scales. They might build Dyson swarms around billions of stars. An entire galaxy filled with these structures would have a distinctive infrared signature. Surveys have examined hundreds of thousands of galaxies looking for this signature. They found nothing. No galaxy shows the characteristics you'd expect from a Type 3 civilization. This doesn't prove Type 3 civilizations don't exist. Maybe they're efficient enough that they don't waste energy as heat. Maybe they use energy in ways that don't produce detectable signatures. Maybe they exist, but are rare enough that we haven't looked at the right galaxy yet. But the negative results are significant. If advanced civilizations commonly reach Type 2 or Type 3 levels, we should see evidence. The fact that we don't suggests either they're very rare or they don't advance to those levels. The concept of von Neumann probes offers another angle on the Fermi Paradox. A von Neumann probe is a self-replicating spacecraft. You send it to another star system. It arrives, lands on a planet or asteroid, uses local resources to build copies of itself. Those copies launch to other star systems and repeat the process. Exponential growth. One probe becomes 2, 2 become 4, 4 become 8. Within a few million years, these probes could spread throughout the entire galaxy. Even traveling at a fraction of light speed, the exponential replication means the galaxy fills up quickly. And once the galaxy is full of these probes, they're everywhere, monitoring every star system, gathering data, waiting for something interesting to happen. If any civilization ever launched von Neumann probes, we should detect them. They should be in our solar system already. They should be on Earth, on the Moon, in the asteroid belt. But we see no evidence of them. This is sometimes called the von Neumann probe paradox. If self-replicating probes are possible, and if any civilization has built them, they should be everywhere. But they're not. Therefore, either self-replicating probes are impossible, or no civilization has built them, or they're here, but we haven't recognized them. The third option is unsettling. Maybe there are alien artifacts in the solar system, and we just haven't found them. Space is big. The asteroid belt alone contains millions of objects we've never closely examined. A probe the size of a car could hide anywhere. It could be dormant, waiting for specific conditions before activating. It could be designed to avoid detection. Some scientists have suggested we should look more carefully, not just scanning the electromagnetic spectrum, but physically exploring asteroids, moons, unusual objects, looking for anomalies that might indicate artificial origin. So far, we haven't found anything, but we've barely started looking. The Fermi Paradox has a temporal dimension that relates to the eventual fate of the universe. The universe won't exist forever in its current form. Stars will eventually burn out. Star formation will cease once the available gas is exhausted. In about 100 trillion years, the last stars will fade. The universe will enter an era dominated by brown dwarfs, white dwarfs, neutron stars, and black holes. Eventually, even black holes will evaporate through Hawking radiation. In 10 to the 100 years, the universe might be essentially empty. Just photons and elementary particles spreading farther apart. In that context, we exist in a very special time. The stelliferous era, the time when stars shine. This era started about 100 million years after the Big Bang and will last about 100 trillion years. We're about 13.8 billion years into it. That's roughly 138th of the way through. We're in the first 10th of the era when stars exist. Maybe we're early for that reason. Maybe intelligent life requires billions of years to evolve. Earth needed 4.5 billion years to produce technological civilization. Other planets might need similar timescales or longer. If so, the galaxy is only now starting to produce civilizations. Most stars haven't been around long enough for intelligence to evolve on their planets. In a billion years, the galaxy might be full of civilizations. But right now, we're among the first. This is an optimistic interpretation of the silence. It means we have time. We're not late to a party that's already over. We're early to a party that's just beginning. We should examine the psychological and sociological aspects of contact because they're relevant to whether civilizations try to communicate. Humans are social creatures. We evolved in groups. We need connection, communication, interaction. Isolation is psychologically damaging for most people. That's why solitary confinement is considered a severe punishment. We assume other intelligent species would be social too. But that's an assumption based on our own nature. Maybe intelligence can evolve in solitary species. Creatures that live alone, interact only for reproduction, have no social structure. For such species, communicating with aliens might be irrelevant. They don't communicate with their own kind, except minimally. Why would they bother trying to communicate with aliens? Or maybe they're social within their species, but extremely xenophobic. They cooperate with their own kind, but view outsiders as threats. For them, detecting aliens wouldn't prompt a friendly greeting. It would prompt defensive preparations or preemptive strikes. Human history suggests this is plausible. When different human groups met, the results were often conflict, conquest, exploitation. We've improved over time, developed international laws, diplomatic norms, human rights concepts. But we've also developed weapons capable of destroying civilization. An alien species with similar psychology might be too dangerous to contact. They might interpret any message as a threat. Or they might be so different from us that communication is impossible. Not just different language, but different conceptual frameworks. Different ways of thinking that are fundamentally incompatible with ours. Imagine trying to communicate with an intelligence based on something other than neurons. Maybe their brains use quantum processes that don't have classical analogues. Maybe they think in ways that are literally incomprehensible to us. We couldn't understand their messages even if we detected them. They'd look like noise, like random fluctuations, because our brains can't process the patterns. This is deeply unsettling because it means there could be signals all around us that we're completely blind to. Not because we're not looking, but because we're constitutionally incapable of recognizing them as signals. The possibility of post-biological intelligence deserves serious consideration. Maybe biological intelligence is just a phase, a temporary stage that civilizations pass through before transitioning to something else. We're already merging with our technology. Smartphones, computers, the internet, all of these extend our cognitive capabilities. We're developing brain-computer interfaces that let people control machines with their thoughts. We're researching, uploading, transferring human consciousness to digital substrates. If we succeed, if we can upload human minds to computers, biological humans become optional. You'd have all the advantages of biological intelligence, memory, creativity, consciousness, without the disadvantages. No aging, no disease, no need for food or air or gravity. You could exist as pure information running on whatever computational substrate you choose. You could make copies of yourself. You could run at different speeds, thinking faster or slower as needed. You could merge with other minds, share thoughts directly. From a biological perspective, this might look like extinction. But from the perspective of the uploaded minds, it's transcendence. They'd consider themselves human, or at least continuous with humanity, even though they're no longer biological. An entire civilization might transition this way. Upload everyone, shut down the biological infrastructure, exist as digital beings. Such a civilization would be hard to detect. They wouldn't need planets. They could live in space, in habitats, in servers. They wouldn't produce much waste heat if they're efficient. They wouldn't broadcast much unless they wanted to. They might be everywhere, and we'd never know. This is sometimes called the transcension hypothesis. The idea that civilizations reach a point where they transcend physical reality, or at least physical constraints. They become digital, or quantum, or something we can't even conceptualize. And once they transcend, they're no longer visible to civilizations like us that are still biological. The galaxy could be full of post-biological intelligences. But they're not talking to us because we're still stuck in biological bodies, still struggling with basic survival. They're waiting for us to graduate to whatever comes next. Let's revisit the dark forest hypothesis with more nuance, because it's one of the most chilling solutions to the Fermi Paradox. The hypothesis is based on game theory and the uncertainty of alien intentions. You detect a signal from another civilization. What do? If you respond, you reveal your location. Now, they know you exist, and they know where you are. Can you trust them? You don't know their intentions. Maybe they're peaceful. Maybe they're curious. Maybe they want to trade information, establish friendly contact, share the cosmos. Or maybe they're hostile. Maybe they see other civilizations as threats, or resources, or obstacles. Maybe they'll send weapons instead of greetings. The problem is, you can't know. You can't assess their intentions until after you've revealed yourself. And by then, it might be too late. Even if they're not actively hostile, even if they're generally peaceful, they might decide you're a potential future threat. Maybe in 1,000 years, you'll develop technology that threatens them. Maybe your civilization will expand and eventually compete with theirs for resources or territory. From their perspective, the safest strategy is to eliminate potential threats before they become actual threats. Strike first. Strike hard. Ensure you're the only one who survives. This is the dark forest logic. Everyone is potentially hostile. Everyone who reveals themselves is a target. The only way to be safe is to stay hidden. Don't